Good morning, dear students. Today is the first practical lesson in the second semester for advanced calculus. And today we are studying basic methods of integration. Let me share my screen. So, no, we will remember some integrals from the table of integrals, differential entry technique, and integration by parts. So first of all, we will use just properties and table of integrals. So let's start. Let's solve exercise 1a. And we have the following integral. Your suggestions how to solve, what to do. Daniel?
We can split these integrals like their brackets.
Do you mean expand, first of all, yeah?
Yes, expand.
And then split. Yeah, actually, this is the main idea. So, yeah, expand in brackets. So when we multiply this bracket by square root of x, what we receive, x square root of x minus x plus square root of x. So done with it. And what about multiplying by 1? We have this. And these brackets are going away. So some components in this expression can be destroyed. So x and minus x, and also with the same with square roots. So now it looks much simpler. Yeah, and I'm reminding you a property of linearity of the integral, so that we can split it this integral to integral of sum can be split to sum of integrals, so like this. So yeah, when calculating this integral, I will just remind you that so antiderivative of such integral is the following. So 1 divided by alpha plus 1 x in power of alpha plus 1, and of course plus constant. Actually, yeah, you must have a table of integrals either in lectures or somewhere else, so you can look at it anytime. What do we have here? So x in power of 3 divided by 2. So we will receive x in power of 5 divided by 2 divided by 5 over 2. So 2 over 5 x in power of 2 and by square root of x. And it will be actually just x and plus constant. Yeah, pay your attention, don't lose constant. It's important for indefinite integrals. Any questions about this task?
No questions.
Okay, if no questions, let's move next. Let's skip B because it's actually the same. So analogically integral, so you need to divide this fraction, so divide these roots by square root of x and then integrate like power functions. But integral c is much more interesting. Okay, your ideas, suggestions how to solve it. How to start solving. What can we do with this expression? Yeah, we have no such integrals in the table, but we can transform it to be a table integral.
We need to transform cosine to x.
Yes, correct. So let's transform it. So cosine to x is actually can be written in the following form. So reminding you trigonometric formulas. So in this way. And now we can use, so we will use the property of linearity of the integral. So removing, so making it sum of, so no difference of integrals. So like this. And now we can simplify them. So I can reduce so this cosine square of x in the first integral. And the same with the sine in the second integral. So what do you see now? Do we have such integrals in the table?
Yes.
Yes. So this integral. So if we integrate this expression, we will receive minus cotangents of x. And this, if we integrate this expression, we will receive tangents of x. But remember about minus before integral. So this is the final answer. So any questions about this task? So firstly, no questions. Yeah, so firstly it looked a bit complicated, but not really. Okay, moving next. So your ideas, how to solve it. Yeah, so we know a table integral, so this integral. So yeah, we know such integral and we can calculate it. But yeah, so it looks a little bit another way. So we need to transform it to such integral. So your ideas, how to do it? Daniel, yeah?
In lecture, teacher said that we need 1 over no, 1 over a number that state near x, and then we need to multiply by u in higher power and divided by 6 in this case.
Yeah, I know, I understand what you mean. But what about this integral? How can it be transformed?
We can write 2x minus 3 in minus fifth power.
Yes, but what the next? Okay. Let me help you. So now we will use differential entry technique. So how to use it? So we need just to make this expression like a regular variable. So how to do it? So we need to receive here, so instead of dx, it must be differential of this expression. So like this. But if I differentiate this expression, I will receive 2 dx. So I need to, so I don't have, so I cannot break the equality. So now we have such integral. I actually can even substitute, so make a substitution like dt, for example, and t here. So now we have a table integral. So do you understand the idea? I know it's not always obvious.
We need to make substitution.
Oh, we can make substitution, or we can even without substitution. So the result is the following. Yeah, so 1 over 6. Stop. Minus 1 over 4. Yeah, so because it's negative power. So 1 divided by t in power of 4 plus c. And now we can return to previous variables. So minus 1 over 8. And like this. So do you understand the differential entry technique, or not yet? So maybe, yeah, we definitely need more practice, but the idea. So if I differentiate it, so I will receive 2 dx. And here I multiply by the 1 second, not to break equality. So any questions or no questions for now?
No questions.
Okay. Now let's solve one more exercise. So exercise E. So analogically, it is solved. So the following integral cosine of 3x plus 5 dx. So again, we need to use the differential entry technique to differentiate it, and analogically. So we need to move under the differential argument of the cosine. So if I do it, so not to break the equality, I need to multiply it by 3, because differential of 3x plus 5 equals 3 dx. So now I can integrate it. So we have usual table integral. So 1/3, and integral of cosine is sine. And that's it. Any questions? Okay, no questions, so moving next. So the following integral dx and so 4x square plus 3. So again, this integral can be calculated with the differential entry technique. What we probably see. So so if this integral is similar to integral of cotangents. So like in the following way. And this integral looks so the antiderivative is the following. So it is similar. So we need to transform this integral to be a table integral. So after calculating which we will receive arc tangents. So here we have 4x square, and we need to move. So 4x square is actually 2x in power over 2. So moving it under differential. And as well, we need to divide by 2, so everything is okay. So now we have a table integral that can be easily calculated. So 1 second. And now 1 divided by square root of 3 and arctangents over 2x divided by square root of 3. Any questions about this task? Okay, I guess that no questions. So let's continue. Let's have more practice. So again, now we are using a differential entry technique for integrals. So task 2a, we have the following integral. So tangents cube of x divided by cosine square over x. So any ideas how to use the differential entry here? So which differential can you see in this integral, under this integral? Daniil, yeah?
At this moment, I think that we can expand tangents at sine over cosine, and probably it helps.
Well, actually, we can make so we can solve it simpler. Maxim?
We can transform 1 divided by cosine square x into tangent x.
We can, but why? So more ideas. So do you see a differential of function under this integral? Okay, after some practice, you will see it. So actually, so what I mean, so dx divided by cosine square of x, it is actually differential over tangents x. So what will we use? So tangents cube of x multiplied by and differential of tangents x. So we just integrate power function. So we don't have to expand tangents like sine cube over cosine cube. So with the differential entry technique, we just transform it to power function, and it is much easier. So, any questions about this task? Okay, so let's move next. Part B. So we have the following integral. So what can be moved under differential here? So how to solve? Your suggestions? Okay, so what do we have in the numerator? It is actually half of differential of this expression that under the square root. Okay, let me just copy and paste it. So this is just so it can be rewritten in such form. So yeah, if we differentiate this expression, we will receive 2x dx. So this is the differential. Yeah, of course, if we differentiate if we differentiate x squared, we will receive 2x, but constant will be differentiated to 0. So we move under the differential all the expression. So now we have again the power function, and so the antiderivative of such function, so 1 over square root is so 2 square roots. And the final answer is the next. So any questions about this task?
No questions.
Okay, so moving next. So the next integral. So what we will do here, we will use the property of linearity of the integral and also differential entry technique. So integral of the sum can be converted to sum of integrals. So the first integral is the table integral. It is integral of arcsine. And what about this integral? So again, a differential entry technique. So here we, so in the numerator, we see something like something similar to differential of the expression under the square root. Why similar? Because we need to do some arithmetical manipulations. So nothing is broken. So now everything is correct, and we can calculate this integral as well. Okay, let me move to the next line. So 1 second multiplied by 2 square roots and plus c. Yeah, and let me remove these fractions. So now it looks like this. Any questions about this task?
Can you explain again, please, where x goes and at second row?
Here.
Yes.
So do you mean this x, right?
Yes, yes.
Okay, so this differential is the following. So if we differentiate this expression, we will receive 2x dx. And here we have so just 1x. So not to break equality, we need to multiply by minus 1 second. So minus 1 second of this differential equals x dx. So have I answered your question?
Yes, thank you.
Yeah, be attentive with the coefficients, don't lose them, so avoid such mistakes. Oh, maybe you have some more questions about C.
For me, no.
Anybody else? Okay, if not, let's move to D. So, the next integral, and while I'm typing, I'm open for your suggestions how to solve it. So, which differential do you see here in under this integral? So, differential which function? So, do you see?
Arctangent.
Yeah, so differential of arctangents. Yeah, so let me write it in under integral. Yeah, so differential of arctangents is the following. So dx by 1 plus x squared. So here we have a differential of arctangents. And now again, we differentiate it like a power function. Any questions about this task? Okay, if no questions, let's move to part E. So, your suggestions about this integral. So, which differential, which function do you see here? So, do you see a differential function under this integral? So, anyone? Daniil, yeah?
I see at this moment only one is tangent. 1
So
over cosine square x.
so differential of tangents, yeah, or something more. Okay. Actually, we should move all this expression under the differential. So we will receive so the same as differential of tangents. So because one will differentiate to zero, will be differentiated to zero. So yeah, sometimes it can be not obvious. So if we move only tangents under the differential, so it will not help us a lot. So, but the better solution is to move the whole this expression under the square root. And now we have a table integral. Any questions about this task?
Sorry, can you explain once again idea of this method? Because for me, I a bit confused. So we cancel this d and integral, sign of integral, and then we have a simple example. Yes.
Yeah, so something like this. We actually can make a substitution. So like this expression equals t. So the integral will be the next. So just t and so by square root of t. So like this. But I skip usually this part. So yeah, we see a differential of the function under the integral. So here is the differential of this function. And if we move it under so if we move this 1 divided by cosine square of x under d, so we have this. So if we differentiate this expression, we will receive this. So this part. Or maybe let me draw. So this differential became this. So nothing broken, nothing changed. Yeah, and we just integrate like a power function, so simplifying it. Have I answered your question, or did you mean something else?
Yes, I understand, and I forgot this rule that sign of integral can cancel with this сплохидное с d.
So you just forgot the how to differentiate, yeah? A little bit
I-
forgot the table of derivatives, right?
No, now I understand everything, so thank you.
Okay, but feel free to ask me if you don't understand it. So maybe we'll explain in other way. Okay, so more questions? Okay, let's move to other task. So f, so the next integral, so dx, and here we have x multiplied by logarithm of x. So what can be moved under differential here? Daniel?
I think logarithm x.
Yes, logarithm x. So it looks like this. So we will receive this expression. differential of logarithm x divided by logarithm of x. So yeah, so this function moved. So 1 divided by x moved under differential, and we receive just a logarithm of x. And now we integrate. So let me just remind you that such integral so is the following. And here we have logarithm of module of logarithm plus c. So any questions about this task?
No questions.
Okay, if no questions, let's have a break for 5 minutes. And after that, we will integrate by parts. Okay, let's continue. So now we are having the next integrals. So x by sine of 2x and x by exponent of minus x and so on. So how to integrate it, it's a question. So actually, yeah, so it's not obvious how to calculate such integrals. So in case of differentiation, it's understandable, but we don't have such rules like so integrating product. But we know another approach like integration by parts. So this is the formula of integration by parts. So the idea is that one component of product is taken as u function and other component is as differential of function v. And then it's calculated in the next way. So uv minus integral of function v multiplied by differential of u. How to use it? So for integrals like this, so polynomial multiplied by exponent, cosine, or sine. So we take u as so polynomial is taken as u, and dv is the differential of exponent or trigonometric function. For integrals like this, so polynomial by logarithm, arcsine, arccosine, arctangents, arcotangents, so we take dv as a polynomial and the differential of polynomial, and u is a logarithm or inverse trigonometric function. Also, we have recurrence integrals. So for such integrals, like so where we multiply exponent by cosine or sine, so it doesn't matter which which part can be taken by u or v. So any of them. And for integrals like this, so cosine of logarithm or sine of logarithm. So we take this expression as u. And now let's have some practice, or maybe you have some questions. Okay, if no questions, they will appear during solving exercises. So let's calculate the first integral. So let's use integration by parts. So here u is x. So u equals x and du equals dx. And what about dv? So dv equals, so actually sine over 2x dx. So differential of this function. And v equals minus 1 over 2 cosine of 2x. So we have everything to integrate by parts. So let's integrate. So first of all, so we have u and uv. So this, and now the integral. So of v du. So we have minus. So minus here, but yeah. So in formula we have minus, but we have minus here, so it will be a plus. So 1 second, cosine of 2x. So we have v, and now du. So dx. And what we basically have, it's almost a table integral. So calculating this integral, and we will receive plus 1/4 sine of 2x plus c. So any questions about this task? Okay, I guess that no questions. So let's move to part B. By the way, so we have here x multiplied by e in power of minus x, but let's make it a little bit more complicated with this. So power of 2, x in power of 2. In such case, we will have to so we will have to use the integration by part twice. So it's like a spoiler. So u equals x in power of 2 and du equals 2x dx. dv is e in power of minus x and v equals minus e in power of x. So firstly u and v, so minus x in power of 2 by exponent of minus x. And the next integral, so I will write 2 in outside of integral sign, and we will have x in power, also x multiplied by e in power of minus x dx. Again, pay your attention to signs, so we have minus here. So again, we received such integral, and we have to apply integration by parts once more. So actually, there is such a rule for polynomials. So so degree of polynomial equals how many times we use integration by parts. So, but we have so here is the power. So degree of this polynomial is less than here. So x square, and here we have just x. So in power of 1. So u equals x, and du equals dx. And the same for v and dv, so nothing changes here. So don't lose this. And now plus 2, and what we have? So minus, so uv minus x by e in power minus x plus so the next integral e in power of minus x dx. Make more beautiful brackets. So I guess, so nothing was lost, yeah. And now we can calculate this integral. This is almost stable integral, so we will move, okay, let's do it like this. So let me remind you once more differential entry technique. So minus x. And now let's integrate it finally. So, and here we will just have the exponent and plus c. So any questions about this exercise? So you understand the idea. So depending on degree of polynomial, so So degree of polynomial equals how many times we use integration by parts. Okay, let's move next. So the next integral, arcsine of x and divided by square root of x plus 1. Yeah, so that's not actually polynomial, irrational function in the denominator, but if we use integration by parts, it will be easier. So the expression will be simplified. So u equals arcsine of x and du equals dx and divided by 1 minus x square. And dv equals the next expression. So dx by x plus 1. By dx by square root of x plus 1. And v equals, so if we integrate it, so 2 square roots of x plus 1. So we have everything to integrate by parts, so let's calculate. So let's see what we will receive. And minus, so minus the following integral. So yeah, let's move to here. So what we have? So now we can just use difference of squares. So let we modify it a little bit. So 1 minus x and 1 plus x. No, not here. Okay, so just to make it more, so make it simpler, so what we have. So now we can cancel these square roots, 1 plus x. So let's do it. So simplified, and actually here we can also use the differential. So we will use differential entry technique for this integral. So this is the differential of 1 minus x. And now let's finally, so let's calculate the final integral. So this part plus 4 by this square root plus c. So any questions about this task? So some arithmetic transforms. Okay, if no questions, let's move next. So now we will integrate our cosine of x. So again, so u is our cosine. And differential of u is minus dx by 1 minus x, by square root of 1 minus x squared. dv equals dx. So v equals x. So now we have everything to integrate by parts, so let's calculate. Plus so plus this, yeah, and x dx. And now we will use the differential entry technique for this integral that we received. So minus, so the following. So differential. Yeah, and also we need to multiply or to divide by 2. So this. So a little bit transformed this integral, but nothing changed. So equality is not broken. And now we can integrate. So, and that's it. Any questions about this task?
No.
No questions.
Okay, so actually, yeah, we don't have table, so we don't have integral of our cosine of x in the table, but we found it. And now let's move next. So recurrence integral, you will understand why it's called in such way. And let me remind you that it doesn't matter which part of this integral can be taken by u and which can taken as v. But what is important? So now let's, for example, take exponent as u. So let's take it. And dv is sine of x dx. And v equals minus cosine of x. Okay, so now let's integrate. Yeah, by the way, for recurrence integrals, always so they are always calculated by parts twice. So no more, no less. You will understand why after that. So yeah, we definitely need to integrate it by parts once more because we have such expression. So exponent multiplied by cosine. And what is important? So if you first time take u as exponent and v as a trigonometric function, the second time it must be the same. So again, so u will be exponent, so nothing changes for this row, and for v, so cosine of x dx, so dv equals cosine of x dx, and v equals sine of x. So that's important. So which you take the first time. So if u is exponent the first time, so it must be the same for the second time. If u is a trigonometric function the first time, the second must be trigonometric as well. So otherwise you will have no success in calculation of the integral. Okay, so this expression remains, and plus this. So e in power of x by sine of x minus the next integral e. So cosine of x, sine of x, yeah, multiplied by e. So, okay, e in power of x multiplied by sine of x, and yeah, of course, dx. So what do you see now if you look attentively at this integral that we received? So look at it attentively. So what happened? Daniil, yeah?
We have the same that we had at start.
Yeah, so actually the same as the initial integral. So that's why it's called a recurrence integral. So your idea is how to find it. So how to calculate this integral, by the way? Yes?
I think we can substitute probably.
So you mean just to mark this integral somehow, yeah? Or
Yes.
yeah, we can do like this. So this integral like I, so mark it as I just for our convenience. And what we have, I equals this expression minus I. So we just have to solve this equation with respect to this integral. Yeah, and finally I equals 1/2 of this expression plus c. So that's why such integrals are called recurrence and why they must be taken always twice. So because after the second integration by parts, we will receive again the initial integral and then solve the equation with respect to this integral. Any questions about this task?
No.
Okay, and now the last integral for today. What's going on? Okay, let me now restart math type. Okay, so now we have the next integral. So sine over logarithm x dx. So how to calculate? As you remember, we take whole this expression as u. So because if we take it as dv, we just we have to calculate this integral. So it makes no sense. So u equals this expression and du equals so 1 by x cosine over logarithm x and dx. So nothing lost. So cosine of the outer function, and so derivative of outer function, derivative of inner function, so everything is okay. And dv equals dx, so v equals x. And now let's integrate. So x by sine over logarithm x minus and the next integral x by this expression. So x is successfully cancelled here. So now again we need to use integration by parts. So again, u equals so cosine of logarithm x, and du equals minus. So 1 over x and sine over logarithm x. Then dv equals dx and v equals x. So continuing calculation. So uv, so x multiplied by cosine over a logarithm of x. Lost the bracket. Damn it. And now plus, because of minus here. So this integral, so 1 of x, lost dx here, by the way. So x multiplied by this expression. And what we receive, so again, we receive the initial integral that we had before. Let's expand brackets, by the way. So for our convenience. So again, the initial integral, and we need to solve the equation with respect to this integral. And finally, e equals 1 second of this expression plus c. Of course, you can move x out of brackets to simplify a little bit, doesn't matter, so that's not the most important thing. But here is the final result. Any questions about this exercise, about previous exercises?
For now, no, but probably they can appear.
Okay, you are always, so you always can feel free to text me in Google Chat, and I will respond to you, so everyone knows about it. Yeah, so either Gmail, either Google Chat, but Google Chat is better, more convenient. So have a nice day. Happy Valentine's Day, by the way. Stay safe and yes. So just have a nice day. Goodbye.
Thank you.
Goodbye.
Goodbye.
Thank you, goodbye.
Have a nice day too. Goodbye.
Thank you.